section of the lecture, we'll delve a bit deeper into the grid infrastructure of today versus what we might expect from the future grid. We'll talk about demand-side management and how it will play an integral role in the structure of the grid of the future. And make sure you post to the discussion board on how close you think we are to achieving that smart grid. So you just watched a video on the smart grid, and as we discussed and as mentioned in the video, distributed networks are distinguished from central station power systems by two key features. One, the electrons move shorter distances, so between where they're generated and where the end users are. And two, that the scale of the generation plants are typically smaller within the system. Those distributed energy resources can vary significantly. They can be what we commonly think of with DG as PV or even wind turbines, but they could also be fuel cells. They might also be small gas turbines or some kind of internal combustion engine. And so for a building or a campus, these types of distributed energy generators might be attractive, and maybe we will then be able to avoid any losses associated due to transmission, alleviate any concerns regarding reliability or security, etc. These distributed generation sources have been used in many countries for a while for various different applications. So let's say you have a really sensitive industrial process, you need a very specific power quality, and you need very high reliability. We might use one of these distributed energy resources for that purpose. They're used for emergency capacity. You can go out to Home Depot and buy a generator. That can be considered a distributed energy resource. And more they're being used to avoid expansion of transmission and distribution systems, as well as the building of new power plants to meet increased capacity. So let's take a look at today's electric infrastructure. There's some kind of centralized power generator, then there's a transmission substation, and a pretty sophisticated transmission control center to look at power coming in from all of the power generation across perhaps a region of the country, and trying to decide where to take that power and put it so that we're always meeting demand with supply. Then the power is transmitted to a distribution substation, and that distribution substation has a pretty good idea of the power needs of the industrial, commercial, and residential sectors in time, instantaneously. And so it's distributing on demand that power. Now, tomorrow's electric infrastructure will look much different. We still have power generation centralized, but we have much different control over that power generation. Instead of just simply going through a substation, we have some kind of regional control center that's not only looking at what's coming in from the centralized power generation source, it's also looking at what's happening on the residential, commercial, and industrial sides more closely. It's looking at those distributed resources that those different industries might have, and it's communicating perhaps wirelessly with all of those systems to ensure optimization. There are things called VAR support systems, the volt-ampere reactive support systems. These systems regulate the voltage. We want to make sure the voltage coming onto the grid is high enough to ensure it can get transmitted and avoid blackouts. We also don't want that voltage to be too high either because of heating conditions that could result in then causing problems. So because now we've got centralized power plus we have distributed resources, we might have power of various flavors going two ways, and that's a very distinct difference, this two-way operation of power. And as a result, we need to be more tightly controlling things like the VAR to ensure that the power quality is good enough to go to these different places. We also have fixed compensation. These are essentially fixed capacitors that are carrying or storing a certain amount of energy consistently. They are there to respond to just light load conditions, right? So we always have some amount of energy available as needed, a relatively small amount of energy available as needed to allow more flexibility on the grid. Also in the figure is the FACTS. This is the flexible AC transmission systems that provide dynamic voltage support, essentially reactive compensation. Again, without getting into too much detail, with this kind of two-way control from all of these different generation sources, we need to ensure that we have a well-balanced quality of power available on the grid. The distributed resources, those can be from PV, right? They can be from the small turbines or generators that we discussed. But also what's important to note here is that we might also have electric cars that are also needing to be charged from the grid. And maybe they are more charged at night when typical power consumption is low overall. And understanding how to balance that best with the grid is important. We also may have backup batteries associated with these different buildings across various industries. And so those backup batteries may be available to us to actually better control and optimize the power on the grid. And then we may have customers that are willing to turn off lights or turn off air conditioning, ramp up the thermostat, whatever it is, to respond to the fact that perhaps demand and supply are not going to be optimally balanced. And as a result, there may be customers that are willing to change their energy usage, either shift it to different hours of the day or just be a little bit more uncomfortable in a little bit warmer temperatures during the summer or certain peak days during the summer in order to save energy, and they'd be compensated for doing that. So traditionally, utilities have been a regulated monopoly, that state-level public utility commissions have been empowered to determine whether new capital facilities should be built or what to set electricity prices at, to ensure that investors who are investing in the infrastructure of the grid receive adequate returns. And this then attracts future investors who are investing in the future grid. Typically, utilities have been have ranged from the municipal to the national level, depending on where we are in the world, and has typically been a mix of public and state ownership and oversight. Now, in the 1990s is when deregulation occurred. The idea was that deregulation of the utilities would lead to improved efficiencies. It started in 1990 in the UK and has infiltrated various parts of the world to mixed results. Some deregulation has led to increased competitiveness and improved efficiencies, even reduced costs, but others haven't worked. And some of that has come from the unpredictability of the supply and demand, of changing fuel prices, of the fact that we have no way to store energy. Because of the lack of flexibility from utilities, sometimes the deregulation and the efforts that resulted have not led to a better system. Interestingly, too, while these industries have been deregulated, many of the public utilities commissions are not allowed to increase the prices too much because of the potential economic impact, negative economic impact that might have on consumers. So it's not really a free market, even though we've deregulated the utilities. It's not really a free market. There are still regulations that are imposed for various reasons. So as the electricity sector has grown, there have been various problems that have arisen. One, problems of meeting peak demand. meeting peak demand because capacity has increased, but new power plants aren't being built, partially because we can't get the investment to do so, or there's not an it's not economically attractive to do so. Utilities have had to come up with more creative ways to deal with peak demands to avoid power outages. So instead of building power plants, utilities have done things like offered cheaper electricity to customers willing to be shut off during peak times, providing services to customers to encourage more efficient electricity use, and also encouraging investment in distributed generation sources to reduce peak demands. There is a high variability across utilities in this country as to what extent these three efforts have been undertaken by the utilities. Some utilities and states are more progressive than others. Some utilities and states have certain regulations that have been imposed, for example, to encourage energy efficiency. So you see a high variability across states in this country. But I think everybody would agree that in the future, we do need to improve the grid. We need to improve our system so that we can instantaneously meet supply and demand. And distributed generation is certainly being looked at as an opportunity to be able to do that in a cost-effective way. If we talk about, if we think about the economics associated with electricity production, certainly the low cost of coal has dominated the price of the electricity that's produced in the industry. So we've talked about externalities associated with coal and perhaps other costs that are not considered in that kind of pricing scheme. There are major sources of uncertainty that are influencing the price of electricity, particularly if other fuel sources are used. But right now, coal prices sort of dictate what is cost-effective electricity and what isn't. In fact, at about $4 per million BTU is the price, sort of the threshold at which if an alternative energy source is proposed and it costs more than the $4 per million BTU, then it's more expensive than coal and likely less attractive for various reasons. And so coal sort of sets that threshold at which we look at the comparative price of alternative ways of generating electricity. Economics are also influenced by a variety of different other factors, such as how much it might cost for the capital cost, upfront costs of some kind of power plant that generates electricity. Certainly the operations and maintenance costs influence the economics. Fuel costs influence the economics, as I just mentioned. Market price fluctuations and uncertainties associated with fuel costs are taken into account in various ways, and large uncertainty, even if costs are low right now, for example, for natural gas, uncertainty associated with those costs influence the overall considerations of the economics of the electricity production. Of course, plant efficiency matters, and that efficiency can vary slightly over time. Without good operations and maintenance of the facility, plant efficiency can suffer. Peak demand, whether or not there are issues associated with peak demand in a particular region, can influence the electricity costs and influence whether or not it's attractive to move to alternative sources. And of course, regulations, which again vary from state to state, are going to influence the economics of energy. And so last, I want to talk about one other energy carrier. We've already talked about electricity as an energy carrier. You can think of gasoline as an energy carrier to make your car go. What about hydrogen as an energy carrier? And I bring this up because a decade or so ago, hydrogen was thought of as the future. Futurists were suggesting that hydrogen would be the major energy carrier of the future, both for centralized or distributed power generation, also for cars as well. So why hydrogen? Hydrogen actually has a lower energy density relative to hydrocarbons found in coal and natural gas and petroleum, but it has significantly lower carbon emissions, in some cases no carbon emissions at all when used as an energy carrier. It is particularly attractive as the fuel for fuel cells and for fuel cell vehicles. It can be stored rather compactly, especially compared to batteries, but it's actually heavier or bulkier than gasoline. Production of hydrogen today is not easy. It's complicated to produce hydrogen from natural gas. We can do it, but it's actually quite energy intensive. So when you do a full life cycle analysis of how much energy it takes to produce hydrogen, that in and of itself makes hydrogen look not very attractive. If it takes more energy to produce overall than coal, then digging coal out of the ground, and especially if we account for all the emissions, the sustainability impact from using that energy to produce the hydrogen, then what we see is that overall it's actually not necessarily as attractive as coal, or certainly as natural gas. But there are innovations to be had, that there's thoughts around producing hydrogen by the electrolysis of water, a rather simple process. If we can overcome various technological barriers, perhaps we could produce hydrogen simply and cheaply to be that energy carrier of the future. There are various concerns associated with hydrogen in addition to costs and the life cycle analysis, safety being one of them. Hydrogen is quite flammable, and so we would have to come up with a way to address the potential flammability of hydrogen. So major investments in technologies, as well as shifts in policies and additional investments, are required in order to continue to move hydrogen along the path of seeing it as a potential energy carrier of the future. Certainly, if energy prices continue to increase, that might make hydrogen more competitive, leading to more innovation and more interest in investment. And hydrogen, we might actually see it, because of its ease of being produced in smaller quantities, we might actually see it being more attractive for distributed generation than for centralized generation. And if we've got the infrastructure in place for distributed generation as a result of enhancements in smart grid, then hydrogen as an energy carrier for those distributed applications like fuel cells might become even more attractive.